So in section 2.2, we're going to talk about differential equations that are separable. And what that means is we can get, if we're talking about equations that are written in terms of x's and y's or dy over dx, we can get all the x stuff on one side and all the y stuff on the other side, and then we can integrate each side of the equation. So something that's separable would look something like this, or could look something like this. So we have some function with respect to x, some function with respect to y. So then if we were to separate that, we could get all the x stuff on one side. Maybe we would start by multiplying by dx on both sides. And then dividing by the h and y. So then we have succeeded in separating, so then we would integrate. And separable equations can take on lots of different forms. We've seen in the videos from chapter 1 that some of those equations were pretty easy to integrate. I think we ended up with a quadratic in one. We ended up with an exponential in one. So just to kind of quickly review some techniques that we may have to use. Anything from Calc 1 and Calc 2 could show up, and typically does show up throughout the course. So some examples. We may have to integrate using by parts. So remember, when we integrate u dv, it's going to be uv minus the integral of v du. So you've got to pick out what u and what dv are, and then you find v and du based on what you pick for those two. So by parts may show up. We may have to use power reducing functions. And this was typically used for trig. So your power reducing formulas, we had one for sine squared. That was equal to 1 minus cosine of 2u over 2. We have one for cosine squared. That's equal to 1 plus cosine of 2u over 2. And then we had one for tangent squared. And that was 1 minus cosine of 2u over 1 plus cosine of 2u. It's really just taking this one and dividing by that one. There's all kind of trig substitutions that could be used. You may have to use one of the Pythagorean identities to substitute, or a double angle formula to substitute if we're dealing with trig problems. We also had trig substitutions where we used a squared minus u squared. We would let u equal a sine of theta. Then the square root of a squared minus u squared was equal to a cosine of theta. We had things in the form of a squared plus u squared. That's where we would let u equal a tangent theta. Then the square root of a squared plus u squared was equal to a secant theta. And then we had square root of u squared minus a squared. And we solved things in that form by letting u equal a secant theta. So then we got a tangent of theta was the square root of u squared minus a squared when u was bigger than a, and negative a tangent of theta equals u squared minus a squared when u is less than negative a. We won't see these very often in this course, but just want to remind you those are things that you talked about back in Calc 2. Partial fractions. Remember, there are 4 forms where we had non-repeated linear, repeated linear, non-repeated irreducible quadratic, and repeated irreducible quadratic. We talked about using the tables and then reduction formulas from the tables. That was a technique that we talked about. We talked about completing the square. That really helped us with some of that, with those inverse trig functions. And then U substitution, which is something we actually started talking about in Calc 1. So all of those are different techniques to help us integrate something. The best place to review some of those techniques would be going back to your calc book and looking at chapter 8. And we are using, remember, Larson's calc book. Chapter 8 where we saw almost every single one of those techniques, starting with that review of U substitutions from Calc 1, and then getting into the trig substitutions and the partial fractions and so on and so forth. So what I want to do now is just look at a few that are separable and do some integration and solve a few. So let's say we have dy over dx is equal to xe to the negative 4x. If we want to solve something like this, we could use that separation of variables. So we would have dy is equal to xe to the negative 4x times dx. And now that we've separated, we can integrate both sides. So if we integrate dy, we're just going to get y. This guy is going to be by parts. And anytime you do by parts, you should show me all of your work. Remember, the formula for by parts is integrating u dv is uv minus the integral of v du. So in this case, we are going to choose u to be x, and we're going to choose dv to be e to the negative 4x times dx. So if we choose u to be x, then the derivative of u is 1 dx. If we choose v to be e to the negative 4x dx, then we have to integrate that to get v. So I'm going to do some side work over here. That actually requires a u substitution. So think about your u being the negative 4x. So if that's your u, your du would be negative 4 dx. We're missing that negative 4 here. We can write it in as long as we compensate with a negative 1/4 out front. So now when we integrate e to the u, we're going to get e to the u. And we're not going to worry about the plus c. That plus c is going to fall out when we finish this. So then by parts says when we integrate this, it's going to be uv minus the integral of v du. So it's going to be u times v. So it's going to be negative 1/4 x e to the negative 4x minus the integral of v du, which is dx. So I'm going to rewrite. I'm going to pull that constant here out. Negative times a negative 1/4 is a positive 1/4. And now we need to integrate this guy, and that's a u substitution as well. Our u would be the exponent negative 4x. So du would be negative 4 dx. Compensate with a negative 1/4 out here. So we're going to have minus 1/16. And when we integrate e to the u, we get e to the u. And then we're going to have the plus c on the end. So there's our solution. Let's look at another one. Suppose we want to solve this equation. Your first step is to try to separate the variables. So let's try to get all the x stuff on one side and all the y stuff on the other side. We can multiply both sides by x. And we can multiply both sides by dx. So we're going to have x square root x minus 5 times dx is equal to dy. So we could use by parts on this, or we could do a u substitution. I'm going to do the u substitution. This actually goes back to Calc 1. We're going to let u be that x minus 5. So the derivative of what we chose for u is going to be the derivative of x minus 5, which is 1 dx. So we have a substitution for this guy, and we know dx is du. We have a substitution for that. We just need a substitution for this. So we need to know, what is x equal to? Well, we can figure out what x is equal to by solving this guy for x. If we were to move that 5 over, we would know that u plus 5 is equal to x. So now we are ready to make our substitutions. So if we integrate dy, that should be equal to integrating x square root x minus 5 dx. But we could substitute in for this x, u plus 5. We could substitute in for this. That was our original u. So now we have the square root of u. And we also know that the substitution for dx would be du. So if we integrate dy, we're going to get y. So now let's deal with this right-hand side. We can distribute the square root of u to both of these pieces. So this would be u square root of u plus 5 square root of u times du. And we could rewrite this. This is really u to the 3/2 power plus 5 u to the 1/2 power. And now we can just use that power rule to integrate. We're going to add 1 to the exponent, divide by the new exponent, and that's the same as multiplying by the reciprocal. Add 1 to the exponent, divide by the new exponent, which is the same as multiplying by the reciprocal. And then we're going to have a plus c on the end. So we have 2/5 u to the 5/2 plus 10/3 u to the 3/2 plus c. Now, ideally, if you can do some factoring, you want to do that just because it's going to make life a little easier if we have to set it equal to 0 and it looks cleaner. Our first step here is to get common denominators. I think that makes it easier to do the factoring process. So we know that the common denominator would be 15. We need to multiply that first fraction by 3/3. We're going to multiply that second fraction by 5 over 5. So now we're going to think about, what do these have in common? Well, we could pull out a 2 over 15 from both of those fractions. And we could also pull out a u to the 3 halves. And a helpful hint here is that you always pull out the smallest exponent. So the smallest exponent is that 3 halves there. Now let's talk about what that's going to leave us with. So we pulled all of the denominator 15 out. If we pull a 2 out of the numerator, that's going to leave us with a 3. If we pull u to the 3 halves out of u to the 5 halves, that's going to leave us with just a u. And you can always check it by multiplying back. If we were to multiply this by this, we will end up with that 6/15 u to the 5 halves. Now, if we pull 2/15 out of 50 over 15, that's going to leave us with just a 25. And notice we pulled out all of the u's. So now we have this answer in terms of u, but remember we started with x's, so we really need to get back to x's. So we're going to make that substitution back. Recall we said that u was equal to x minus 5. So let's substitute that in. So y is going to be equal to 2 over 15 times x minus 5 to the 3 halves times 3 times u, which is x minus 5, plus 25 plus c. So we're going to have 3x minus 15 plus 25 is 10 plus c. So there's our final answer. So let's do a different problem. Suppose we had dy over dx is equal to 1 over x squared minus 9. We can multiply both sides by dx. And now we are ready to integrate. So when we integrate dy, we're just going to get y. This guy could be rewritten as x plus 3 times x minus 3. And this is going to use partial fractions. So we need to figure out, how can we rewrite this? Now notice both of these are linear terms, so that could be rewritten as a over x plus 3 plus b over x minus 3. And I like to do partial fractions by setting up a system of equations. So I think about, and I'm going to space this out. I think about, what's that common denominator between these two? And it's always got to be this guy, right? So this fraction needs an x minus 3 to get that same denominator. This fraction needs an x plus 3. Now, for the left-hand side to equal the right-hand side, since they have the same denominators now, then the tops have to be equal to each other. So at this point, here's what we have. Since they all have the same denominator, the only way this fraction can be equal to the sum of those fractions is if the tops are equal to each other. So that means we have reduced this to 1 is equal to a times x minus 3 plus b times x plus 3. And this is where we can compare coefficients. So if we were to FOIL this out, we would have that. So we're going to compare coefficients of x, and we're going to compare those constants. Because the only way that this side can be equal to this side is if we realize that this is really a 0x here, and the x term over here, which is 0, has to equal to the sum of the x terms over here, which is a plus b. And then the constants have to match up on the left and on the right, which means that that 1 has to equal to negative 3a plus 3b. So we've got a system of equations. We could pop it into the calculator, do RREF. That's going to give us the identity. This is a 2 by 3 matrix. And I got negative 1/6 and 1/6. So what that means is, let me erase this to clean it up. This A would be a negative 1/6, and this B would be a 1/6. So this side would be equivalent to integrating negative 1/6 over x plus 3 plus 1/6 over x minus 3. So when you're doing these types of problems, I do want to see all of your work for partial fraction decomposition. I think that's important. And I'm going to factor that negative 1/6 out. And that's going to leave me with 1 over x minus 3 minus 1 over x plus 3 minus 1 over x minus 3. So both of these are going to integrate using ln and u substitution. This is going to be the ln of the absolute value of x plus 3 minus the ln of x minus 3. And then we have a plus c on the end. And remember, all of this is equal to y. Now, we can put these together. This is the ln of x plus 3 over x minus 3. So, there's our final answer. So, that's an example of partial fractions. So, let's look at another one. We have dy over dx equals xy plus 3x minus y minus 3 over xy minus 2x plus 4y minus 8. So this one, when you first look at it, it doesn't look like it's something that you can separate. But if you start playing with it, you actually can separate this one. So my first step would be just to kind of cross multiply, get rid of the fractions here. So we have xy minus 2x plus 4y minus 8 times dy is equal to xy plus 3y minus y minus 3 times dx. So now we're going to do some factoring. If we were to factor an x out of those two terms, that's going to leave us with a y minus 2. And if we were to factor a 4 out here, that's going to leave us with a y minus 2 also, which is great because now we can do factor by grouping. These terms have a y minus 2 in common. And if I factor that out, that's going to leave us with the x plus 4. So we're going to do the same kind of thing on the other side, and let's see if it works out. So if we look at these first two terms, we could factor a y out. If we look at the second two terms, we could factor a negative 1 out. I wrote that wrong. Factor an x out, leave us with y plus 3. Factor a negative 1 out, leave us with y plus 3. And now if we look at these two, they have a y plus 3 in common. And that's going to leave us with x minus 1. So now let's get all the y stuff on one side. We have a y minus 2 here times dy. Let's divide both sides by that y plus 3. And then let's get the x stuff on the right-hand side. So we've divided by that term. So now we have x minus 1 times dx in the top. And if we divide both sides by the x plus 4, we have separated the variables. So if we look at this, now we are where we can integrate. But notice the degree of the top and the bottom is the same on this left-hand side and on this right-hand side. That means we're going to have to do some long division. So let's go over to the side and let's do that. Let's take that y plus 3 and divide it into y minus 2. And so if we do that long division, y goes into y one time, minus, multiply through. The y's cancel, we're going to be left with a negative 5. So this guy on the left is equivalent to 1 minus 5 over y plus 3. And we're going to do the same kind of thing on the right. So we're going to have 1 minus 5 over x plus 4. So if we integrate both sides, we're going to have y minus 5 ln of y plus 3 on the left. And then x minus 5 ln of x plus 4 on the right. And I'm just going to put the plus c on the right. So let's see if we can rewrite this using exponential functions. So I'm going to move all the ln stuff to one side and everything else on the other. So I have y minus x minus c. That's equal to 5 ln of y plus 3 minus 5 ln of x plus 4. So we know that 5 is really the exponent on the y plus 3. And then we can rewrite this using log rules. So this is really going to be y plus 3 over x plus 4. And both of these are to the 5th. And we are still taking the absolute value. And that's equal to y minus x minus c. Now let's rewrite it as exponentials. The base is e. The exponent's going to be y minus x minus c. And that's going to be equal to all this fun stuff. Y plus 3 to the 5th over x plus 4 to the 5th. So we can rewrite that left-hand side, kind of undoing that combination of putting those bases together into one, undoing that exponent addition in the top. Now, e to a constant, still a constant, so I'm going to call it C1, just to denote that that's a different constant than what we started with. So now we have C1 e to the y e to the negative x times x plus 4 to the 5th is equal to y plus 3 to the 5th. And I don't like to leave negative exponents, so we could move this term to the other side. And when we do that, it would become positive. We would divide both sides by e to the negative x and then move it to the numerator from the denominator. So there's our last example. There's our solution. So this section is really all about just revisiting different techniques and how to integrate from Calc 1 and Calc 2.